Hello and good day to everybody listening into this presentation. I am Adithya from Penn State and I'm happy to talk about our work that opportunistically leverages the underused CPUs while serving deep neural network models on GPUs. We call our serving system as surplus as it leverages the surplus resources available on a heterogeneous server. Most modern applications today are created under the large umbrella of artificial intelligence and machine learning. They are used to solve some of the cutting edge problems of today for diverse fields ranging from health, food and agriculture to retail and education. Specifically, deep neural networks have become commonplace and are in a continuous phase of evolution with models with different characteristics emerging on a continual basis. They target hard problems in computer vision, natural language processing, speech recognition, etc. Let's say a deep learning developer wants to develop a new DNN model. He or she first authors the model on their favorite ML framework like TensorFlow or PyTorch and trains them using the dataset that they have carefully constructed. The training process itself is computationally demanding and is often wholly executed on the GPUs. In this work, we are interested in the part that comes after the training, that is the inference, where he or she deploys the model as an inference service that is, typically a user-facing service. And these services are built using different runtime engines. And in this work, we consider ONNXRuntime, which is an open source runtime developed by Microsoft that is widely deployed under various production settings, but are understudied in academic circles. While training is important and challenging, we see that inference is a growing workload within the data center, with more and more applications starting to use DNN as part of their pipelines. To give some background first, let us look at a simplified view of how a DNN inference is executed, right? So let us consider a very common DNN model, the ResNet50 model, which is used as an image recognition application. And here we see a small portion of the model, shown using the ONNX format. ONNX or ONNX or Open Neural Network Exchange is a powerful industry standard mechanism to represent deep neural networks. So it represents the model as a data flow graph of kernels or operators, along with their weights corresponding to each operator. These operators are, you can think of them as individual tasks. They are individual nodes in the graph, and examples of these include things like convolution and batch normalization, etc. And a deep learning model itself is a data flow graph of such operators. And one can think of operators, kernels, tasks interchangeably, and we sort of use them interchangeably in this work. So an inference runtime basically takes this graph of operators that is constructed after training and performs various compiler optimizations like constant folding, fusion of operators, and things like that, and then constructs a topological ordering of the graph for execution, right? And then the runtime takes this graph, this topological ordering, and generates a sequential execution plan to execute these operators on appropriate heterogeneous hardware, be it the CPU or the GPU or a combination of those two. And the key goal in this endeavor is to actually determine how we leverage all available devices, that is the CPU and the GPU, to extract maximum performance in terms of latency and throughput. And in this work, since we are user-facing, we are targeting user-facing applications, the goal is to minimize the latency and maximize the throughput. This sequential execution mechanism that we just described, obviously works well for linear models like ResNet50, but for emerging models like faster RCNN, which is an object detection model, which is inherently larger, it's more complex in its graph structure, as you can see in this small snippet. The sequential execution is not necessarily the optimal way to run them because they are wide graph structures. Because of this wide graph structure, tasks actually end up spending more time waiting for the GPU than actually executing on them. Recall that they are sequentially executed. So as you can see in this graph, which shows the cumulative time of all the tasks on the log scale for queuing, that is the time spent waiting for a device, and service, which is the time spent actually running on the device. They are widely different for ResNet 50 and faster RCNN. So for wide spanning data flow graphs, the queuing time is a magnitude higher than the service time. And all of this, wants to see what we can do about these wide spanning graphs. And this motivates us to study whether we can concurrently execute some of these waiting tasks which are waiting for the GPU and move them to the CPU. Because at this point of time, like all tasks are just slated to execute on the GPU. The CPU is mostly sitting idle and underutilized and is just used to launch tasks on the GPU. Note that we do not want to move the entire model to the CPU because fundamentally many of these tasks are heavyweight and they actually utilize the GPU very nicely, and if they are just blindly moved to the CPU, they are going to suffer from tremendous slowdown. So that would not make sense. So to summarize, the problem statement that we want to tackle is to perform a heterogeneous inference serving of deep neural networks. That is to come up with a lightweight mechanism or method to partition the graph and place tasks of the graph that reduces the overall inference time of the model. And towards this, our intuition is to see that if we can come up with a strategy that leverages the CPU effectively in addition to the GPU. Not that today's inference runtime just assume that everything should run on the GPU and just attempt to execute them on the GPU. And this is obviously not an unseen problem. People have been dealing with graph partitioning for a long time, and it is intractable. So we would prefer solutions that are easy to implement, they are fast and easily adaptable to the inference runtime itself. And recently the learning community also has taken an interest to this problem, especially Google, trying to partition and place models across multiple devices, more so from the perspective of training. In evaluation, I'll compare against an optimal solution after constructing this problem as a constraint optimization problem. The constraint optimizer itself, takes a long time to arrive at the solution, and we would like to explore fast heuristics in order of seconds or a few minutes that can easily be ported to an inference runtime. So recall that for a single inference execution, we are executing the tasks of the graph on these devices. We first start with a simple policy that moves these queued up tasks to the CPU. We don't move all tasks, but just move those tasks that can finish earlier than they would have completed on the GPU. And we call this as a queuing delay based scheme. We notice that actually moving these tasks queued up on the GPU to the CPU moves the bottleneck to the CPU. So you can clearly see that in this Gantt chart, the execution time actually increases over the baseline execution time. And the reason for this is, as we can see in this table, which shows the average queuing time on the CPU to increase manifold. So in effect, it just moves the bottleneck to the CPU. And this is mostly because a lot of these tasks incur a lot of slowdown, and there are downstream effects of those slowdown for further tasks that are running on the CPU. So obviously this makes us wonder if we can just select tasks that do not suffer a lot of slowdown, and turns out that there are actually quite a few tasks like that. So if we look at this graph, which shows a scatter plot of of each tasks, their service time on the GPU and the slowdown it experiences as it moves to the CPU. So we can see that a lot of tasks suffer slowdown, but there are some tasks that actually do not suffer slowdown. And most of these tasks are tiny tasks, tiny microsecond tasks, which actually do not incur a lot of slowdown when it moves to the CPU. So, obviously moving these tasks to the CPU will not incur a lot of slowdown. So we implement this policy and we observe that that CPU execution time is not so bad. It turns out that these moving short tasks may introduce a lot of memory copy operations. So recall that the CPU and the GPU are sitting across a PCIe bus, and if there is a task's predecessor is on a different device, the output of the tasks need to move across this PCIe bus, and that will incur memory copy operation. So moving short tasks may introduce a lot of memory copy operation, and we can see that this is significantly high for the SD scheme. And this brings us to the heuristic that we propose, basically that starts with the SD-based placement and avoids moving those tasks that introduce a large amount of memory copies. So we start with the SD-based tasks and iteratively prune them based on the amount of data copy that they will incur and compare it to the savings in the execution time, if any, that they might bring about. So based on this heuristic, what we do is we iteratively prune tasks that are moved to the CPU and see if they are going to incur a lot of communication, and if they do incur a lot of communication, we're just going to move it back to the GPU. And we see that this actually is straightforward, and it improves the execution time. And these are the tasks that it actively avoids moving to the CPU. So this so avoiding moving these tasks by the COM plus SD heuristic will reduce the communication cost from 34 milliseconds that we saw before to around 6.2 milliseconds. And turns out that this is very good and reduces the execution time to be more profitable over the baseline execution time. So in this Gantt chart that you can clearly see, the CPU is executing tasks concurrently with the GPU, and the mem copies are not becoming a bottleneck. So in essence, this is the heuristic, and it, as I will show, this actually works not just for the faster RCNN model, but for few models that are wide spanning in their data flow graphs. So the story does not just end with generating good placements. We need an optimized execution engine that can actually run those tasks efficiently in parallel across the CPU and GPU with minimal overheads. And it turns out for these DNN tasks or operators, these are microsecond scale, and the performance impact of even tiny optimizations seem to go a long way. So Surplus is implemented on top of ONNXRuntime. It takes the model in the ONNX format and runs the placement heuristic that I just described and comes up with a device-specific execution plan and uses device-specific backends for each task. So this device-specific backend can be like a CUDA kernel, an OpenMP code, depending on the device itself. And second, there is a tensor memory manager that actually allocates tensors for each of these tasks, be it the weight or the input or output tensor, and it allocates the appropriate, it allocates memory on the appropriate device memory. So it has a straightforward device for executing the model itself. So it uses device-specific queues onto which the tasks corresponding to the device is enqueued. The device executor simply dequeues tasks from its own queue and executes them. And once a specific task is complete, downstream tasks can be marked as ready, and they are triggered onto device-specific queues. There are a few key features that are worth highlighting. So first, we started with a straightforward implementation using mutex locks for synchronizing between these device queues. And notice that they were actually imposing performance overheads for concurrency. So these tiny overheads for each task was introducing a snowball effect, and sort of it actually was creating a worse performance than the baseline. So we replaced them with atomic variables to store the dependency between tasks, and we used a lock-free concurrent queue implementation for the device executors itself. And so essentially using atomics improved efficiency and also was scalable. Second, we detect linear subgraph chains in the model, and we simply execute them using the same executor without letting them into the concurrent queue. This avoided context switches between the threads and also reduced the contention amongst the threads. And most importantly, this enables us to be performant for linear data flow graphs, which is, many traditional DNNs look like that. So surplus can be just plugged into existing deployments, without imposing any overheads for serving linear DNNs. Finally, as I just mentioned, there is a tensor memory manager, which is a higher level memory manager that allows reuse of memory regions on individual devices, because you don't want to perform or host or device-based mallocs in the critical path. So we make the memory manager concurrent proof so that it can enable memory savings. So most importantly, without these optimizations, we actually saw a 16% increase in latency and a 4x memory usage, worsening of memory usage. And this sort of highlights that it's not just about the placement policy itself, but actually these, we need to do careful system orchestration to derive the benefits of those placement policies. So we evaluate our placement approach and and surplus on 4 different platforms with 3 different emerging models with wide spanning data flow graphs. We will compare 4 schemes, starting with the baseline ONNXRuntime system that's used in production with all of its bells and whistles performing sequential execution. We'll compare it to surplus, which is running heterogeneous concurrent execution with the complex SD-based placement that I just spoke about. And in addition to this, we will compare 2 schemes with an optimized placement solution generated by formulating an MILP-based optimization problem. The paper itself, contains the details of the formulation. In this case, we just obtain the solution of the MILP and execute it on both the baseline or ONNXRuntime system as well as our surplus-based system. In this presentation, I'll sort of just focus on the results from the first platform. So, as you can see, surplus provides both mean and tail latency benefits over the baseline ONNXRuntime system. The mean latency is shown on the left and the tail latency is shown on the right. As you can see, the ONNXRuntime shown in the black dashed line, and surplus is shown in the red solid line. And surplus provides good savings in latency both at the low load regions as well as the high load regions, and it also gives you benefits at the tail. There are 2 key points to note. First, the optimal placement is just marginally better than the complex SD based placement. There is about like 3% gain using the optimal placement. And secondly, the optimal placement alone is insufficient to leverage the CPU effectively. So if we put the optimal placement with the baseline execution scheme, it's not going to be any good. It's going to perform worse than the baseline ONNXRuntime system itself. So you do need the system optimizations even if you are able to come up with a really good placement policy. And second, leveraging the CPU improves the throughput as well. As you can see, comparing ONNXRuntime with surplus, we see that there is appreciable gains in the throughput. There are again 2 key points to note here. First is there is an improved utilization in the GPUs in addition to the CPU. So obviously when you move tasks to the CPU is going to be used more, but then by moving all these short tasks to the CPU, the GPU's utilization also improves. And the benefits of surplus scales with multiple GPUs, and we were sort of able to validate that as well. So, I want to leave with a summary and some key takeaways. The first thing is we started with how today's inference runtimes basically do a sequential execution of the DNN model, and it works well for linear data flow graphs. But emerging models like faster CNN have wide spanning data flow graphs, exposing opportunities to parallelize them between the CPU and the GPU. And we propose a concurrent execution strategy where we're going to opportunistically overflow waiting tasks to run on the CPU. And we observe that not all tasks equally slow down, and there is this cost of communication that needs to be considered. So we consider both of these together and come up with a simple heuristic that provides appreciable gains in execution time. And it turns out that to realize the benefits of that placement policy, we have to do careful execution in the microsecond scale by using atomics and lock-free data structures. Sort of I welcome you all to read the paper. There are more results in the paper comparing it with TensorRT and so on. And there is also an optimization model that is used to construct optimal placements. And if you have any questions, please reach out to me. I wanted to thank the organizers for giving me this opportunity to present virtually. It was unfortunate that I was not able to come in person and present it. And I want to thank Professor Frank and Professor Vicky for giving me this opportunity to present it virtually. And thank you all for listening in.
Okay. Adithya, great. You can see you're on top.
Yeah.
Yes, okay, you're with us. Thank you. So, any questions for Adithya? Mickey?
Hi, Adithya. Very nice work. Thank you. Could you say a few words about the effect of the single thread performance of the CPU on the benefits here?
Yeah, I think that does play an important role. Like what I saw between like a server class CPU versus like a desktop class CPU, the gains were higher with a server class CPU, right? They are more powerful. They have AVX units and things like that. And in general, the single thread performance seems to help a lot. So it does play a role, and it does seem to help. Uh, like if you look at the paper itself, there is like a desktop class CPU that I compare with, and a server class CPU, and the performance was higher with a server class CPU. So yeah, does that answer your question?
Yes, thank you. I'm just very curious about what would happen if you try the same kind of work on a mobile CPU, where both the CPU and the GPU are actually quite weaker, and that would be very interesting to me. All right.
Yeah. I think that would be interesting as well. Yeah, and in fact, there are it makes it different in the sense that they are comparable in the performance as well between the CPU and the GPU, as well as there might be some shared memory system where the memory is going to be shared between them, so the communication cost is not as high. So running these actually running faster RCN on the mobile GPU with this sort of an overflow architecture might be better. Yeah, it might be interesting to look at. Yes, I agree.
Thank you. Just one more question. You had a really surprising result there where the results even improved when you had more GPUs, and I would expect that you needed to make better use of the CPU. So I thought it would be worse when you had more GPUs.
That's true. That's because the parallelization that I do there is independently across the GPUs. It's not like a single model is using both the GPUs, but there are multiple instances of the model running on multiple GPUs. So it's just that it's scaling. That's it. That was just more like a scaling result than anything. Yeah, that's why I just put we mostly compare the throughput over there.
Okay, thank you very much.